So I'm gonna report on some results from the SOFIA Atmospheric Observatory. This is a project that was started by Casey Honeyball for her PhD thesis. So Casey's insight was that water ice has got a fundamental absorption out in the 6 micron region that's not accessible from the ground because the region is absorbed by water vapor in the atmosphere. But Sophia is able to fly above most of the water vapor in the atmosphere, and so we can get at that feature. So the advantage of this particular feature is that it's unique to the water molecule, whereas at 3 microns, OH can attach to a number of metal or cations or silicon and mimic the appearance of pure water. So there's some ambiguity that's not inherent in the 6 micron region. We find this absorption feature in all over the solar system and in the literature. This is data from Schweili's PhD thesis, and you can see at 6 microns, you can see the little dip. These are water-bearing Morb glasses, and then in the plot to the lower left, that just shows the relationship of the 6 micron band depth and the 3 micron band depth. It's not a linear relationship, and the 6 micron band kind of poops out before the 3 micron band. It's a fair amount weaker than 3 microns. And so you have to pay special attention to using this. It's been detected on Mars. The plot on the lower left, there's a little bump there at H2O near 6 microns. In wave numbers, it's 1550. And this is from Steve Ruff's paper in 2004 about zeolites, but this is the depth of the 6 micron feature on Mars. We also think we see this in asteroids. This is Spitzer spectra of asteroids from Marchi et al. And you can see it at 6 microns. There's a little emission bump in a bunch of these asteroids. Here's some data that Carl Hibbets obtained for Dries Takir's paper in 2019. So these are vacuum desiccated meteorites. The one with the strong 3 micron band is out of the box. It has a nice 6 micron band, but when you vacuum desiccate it, the 6 micron band goes away, and all that's left of the 3 micron band is the hydroxyl absorption. But recently, there's a paper from Kiro Wilk at Brown where they did some desiccation experiments using Apollo soils, and they didn't see any obvious variations at 6 microns as they dehydrated these soils. So I think there's a lot of work to be done in the lab with these in this wavelength region. But let's get to SOFIA. So one thing I want to emphasize first is that the feature we observe on the moon from this observatory is very weak. So the typical peak height, this is a few 100,000 spectra, is about 2%. We don't see any spectra stronger than 4%. And there's a significant population that show no band at all. In the background are just some examples of this 6 micron peak that we observe. Okay, so this project was to take a large data set and then look for regional variations as opposed to some of the high spatial resolution analyses that have been done before. So the subset of the data that we took is shown in this map. The black outline shows the Maria. Red patches are data taken over Mare regions and blue patches over highlands. The data are very incompletely sampled in space and in parameter space. So here's what it looks like in latitude in the horizontal axis and temperature in the vertical axis. So we have to be very careful when we examine these data that we aren't introducing correlations. So the approach that I've been taking is to limit the data in both latitude and temperature. Early inspection of the data shows that there's temperature and latitude effects, but they could be cross-contaminating each other. So these blue lines are, we take a strip across the data where we try to maximize the extent of a particular parameter while minimizing the extent of the others. So I'll be showing you plots that include these constraints. So we see very strong variations in the 6 micron band depth with latitude. So on the left, we've converted this to water concentration using Casey's calibration. And you can see up to about 50, 60 degrees latitude, we go from a very low water abundances up to a factor of 3 or 4 higher. We also see a temperature variation when we constrain for latitude. So this is a mid-latitude data set, and the water concentration has a strong dependence on temperature. Not surprisingly, we also have a time dependence, a time of day dependence, since time of day and temperature are correlated. We looked at several other parameters. We don't see any clear dependence on solar wind flux or fluence, but just as a caveat, those data are using the average data set over the other Artemis mission, and the actual solar wind flux and fluence varies from day to day and from year to year. So the jury's still out on that. Okay, so the latitude dependence, we think we see a latitude dependent component. It's probably axially symmetric, and what we think is we're following the model of Jones et al. So that's Tom Orlando and Brant Jones. So they say that OH is formed at low latitudes from solar wind, that OH is eroded by, not recombinant, by associative desorption to H2O. That H2O is ballistically transported to higher latitudes. When it impacts the surface, it desorbs to reform hydroxyl. And this is a plot from one of their early papers just showing the gradient in hydroxyl towards the pole. What we've added, or what we think is going on with the SOFIA situation, is that the OH pattern that from the Jones paper is impacted by micrometeorites, where it forms and traps H2O in glass, and this is an application of the observation by Zhu et al. That impact simulation, micrometeorite impact simulation can form water vapor, and we're claiming that that could also sequester glass in H2O, sequester H2O in glass. The time of day and temperature dependence, I think this is a major problem in lunar science, not just at 6 microns, but 3 microns. If the temperature dependence implies that there's continuous source of water, and where can that be coming from? That there just aren't any sources that are big enough that can account for the mass that we're moving in and out of the regolith. The amount of mass to account for this is very large.
One minute left.
Copy. Abby Flom will be talking about this quantitatively later today. And there's been a suggestion that possibly the water that and the 3 micron and 6 micron signal may be sensing some water that's migrating vertically in the regolith and is somehow isolated from the exosphere. So in conclusion, we see a latitude dependent that's consistent with Jones et al. If we throw in a little drip of Zhu et al. The temperature and time of day dependent appears to be inconsistent with Laddie and Lace, Apollo 17 experiment on the surface, and may demand a new process to explain it. And just as throwing it out there, we could repeat this 3 and 6 micron surface of the moon from a CubeSat in Earth orbit. There are a lot of issues with the incomplete sampling of SOFIA that we could solve from a space mission. Thank you.